Welcome to session 2 of unit 4. This session would introduce you to nuclear traces. By the end of this session, you should be able to identify nuclear traces. Let us begin by looking at radioactive traces. Radioactive traces are said to be substances that contain radioactive atoms that can allow for easier detection and measurements. These radioisotopes can be detected by means of electroscope or an electrometer or the Geiger-Müller counter. A typical example of a radioactive tracer is when one of the hydrogens of water molecule is replaced by a tritium. The tritium is an isotope of hydrogen. Now this water molecule that contains the tritium is referred to as a radioactive tracer. The tracer molecule behaves in almost the same way as the normal water molecule. The main difference between the tracer molecule containing tritium and the normal water molecule is that the tracer molecule continually gives off radiation that can be detected with a Geiger counter or some other type of radiation detection instrument. Let us look at application of traces. Traces can be applied in several ways. One of the ways is to use them in the detection of how fast water molecules are taken up by different parts of plants. So let's try to explain that the tracer molecule could be used to monitor plant growth by watering plants with water that contains the radioactive tracer. So in this case, this water contains the tritium isotope. The plant will take up the water and use it in its leaves, roots, stems, and every part, like how it uses normal water. It will be possible to find out how fast the water molecules move into any part of the plant by passing the Geiger counter over the plant at regular intervals to see where the water had gone. So this tracer will be giving off radiations which can be counted by the Geiger-Müller tube, and it will help us to know where the water has reached in the plant. And so the radioactivity can therefore act as a tag or label that allows studying the behavior of the elements or compounds which contain these isotopes. An isotope added for this purpose is known as a radioactive tracer. In this slide, we shall be looking at the uses of traces. These radionuclear traces are very important in human lives, and they are used in several ways. One of the ways is to diagnose many diseases in medicine. Example, the arsenic 74 tracer is used to determine the presence of tumor, and sodium 24 tracer is used to determine the presence of blood clot. In medicine, these radioactive traces are usually taken orally or injected into the patients, and special cameras are used by the medical professional to track the activity of this tracer in the human system and the interaction of these traces with certain sugars and proteins in the human system. And based on that, they are able to interpret and diagnose the issue surrounding the patient. Radioactive traces are also used in agriculture. The radioactive tracer is given to the plant and then in the form of a fertilizer, and the extent to which the plant is able to take up this fertilizer is monitored. So basically, the radioactive tracer in the form of phosphorus fertilizer helps to reveal how phosphorus is absorbed by plants, and this helps in the improvement on the quality of fertilizer and also to know if the fertilizer is effective or not. Another application of radioactive traces is the use in the industry. So the radioisotopes are used in the industry to determine leakages in underground oil pipelines or gas pipelines and water pipelines. To do this, a radioactive tracer is injected into the pipe and a radioactive detector is used to monitor the movement of the radioactive tracer. So at a point where there are several signals indicates that there is a leakage at that point. Another important application of tracers is in analysis. So there are several analytical procedures that make use of radioisotopes or radioisotope tracers. And a typical example is when you want to analyze the amount of a substance that is absorbed in a particular reaction. A small amount of radioisotope is used to mix the inactive substance, and the activity is studied before the reaction and then after the absorption reaction. So if there is a fall in the activity, that gives the amount of substance that has been absorbed. The tracers can also be used as rays, and they are used as rays to disinfect food grains and to also preserve foodstuffs. For example, onions, potato, fruits and fishes, when irradiated with rays, can be preserved for a longer period. In this slide, we will be looking at preparation of tracers. For a tracer to be able to give the needed results, it must be able to live long enough in the system in which is being used. Some examples of radioactive tracers are the palladium, thorium, and some other radioactive tracers, and they are able to live long enough in the system so that analysis can be carried out. To prepare tracers, one, we can extract them from their natural ores, and examples are the lead and thorium. We can extract them from their natural ore. We can also prepare tracers by the bombardment of a specific nuclide with a suitable target, and this can be done in a nuclear reaction or by the use of cyclotron. Now the cyclotrons are protons or even deuterons and other heavy ions. We can also get some of these radioactive tracers by separating them from fission products of uranium. In this slide, we shall be looking at how to prepare radiochemically pure zinc 62, which has a half-life of 9 hours. So to do that, a copper-rich target is irradiated with photons. This copper-rich target contains isotopes of copper. Sometimes when this copper-rich target is irradiated with these photons, radioactive copper as well as zinc isotopes are produced. So zinc 62 that is produced in the process, which has a half-life of 38 minutes, will decay to produce copper 63, and this happens by electron capture. In the electron capture process, the nucleus absorbs an electron which converts a proton to a neutron. The copper that is produced in this process is separated from the bulk of copper target. 2 hours after the irradiation, the target will be dissolved in nitric acid and the pH will be adjusted to about 3. This causes copper to precipitate as copper sulfide, and the solid copper sulfide that is produced is filtered. The filtrate will then be boiled so that it will become concentrated, and also to drive off any hydrogen sulfide that is present. The only component that will be left in the filtered In the concentrated filtrate will be the cation zinc 2 plus and the hydrozonium ion. The solution will then be electrolyzed between platinum electrode and radiochemically pure zinc 62 will be collected at the cathode. You have here some few self-assessment questions for you to try your hands on.